Hi, my name is Samina Abdullah. I am a senior studying computer engineering in business, and my honors capstone was an electrooculography-controlled cursor through the course EECS 458 or BME 458, which is biomedical instrumentation and design. My advisor was Professor Barry Belmont, and I worked together with Aiden Ahamparam, Ellie Dolzo, and Sammy Ismail on this project. So I'm going to start with what is electrooculography? Electrooculography is a technique for measuring the corneoretinal standing potential that exists between the front and the back of the human eye. Here's a little diagram showing how eye movement translates to a voltage spike, which you can measure through electrooculography. So you can see in the middle eye movement, when the eye looks up, the voltage spikes up, and when the eye looks down, there's a spike in the negative direction in the amplitude of the EOG signal. So our objective for this project was to build a device that allows users to operate a computer via the movement of their right eye as opposed to hand motion. And this technology would be particularly useful for amputees, quadriplegics, and any individual unable to operate a typical mouse. Another reason why this project is so important is because computers have become increasingly important in everyone's daily life. So having a way for this audience to be able to use a typical computer mouse is especially useful. So to start off, I'm going to go over how we place the electrodes on the face to be able to acquire our EOG signal. So we put two electrodes, one on the left of the face, one on the right of the face to acquire a horizontal eye movement signal. And then we put an electrode on the top and bottom of the right eye to acquire a vertical signal. And then we also had a grounding electrode, which we could place anywhere on the forehead. Here's a diagram of our high-level experimental setup. So first we placed the electrodes on the user's face, and we connected those electrodes to our breadboard. Those signals then went into an isolation circuit that will protect the user from any unwanted current or voltage spikes. Those signals then go into our DAC, which then formats the signal so that it can be acquired by our computer, and we process those signals in LabVIEW. Here's a picture of our breadboard. It was a pretty simple circuit, but you can see these unconnected wires are where we connected the electrodes and the outputs of those signals to our isolation circuit, which went into the DAC and then into our computer. Here's a schematic of our horizontal circuit. Our horizontal and vertical circuits look basically the same, except for the fact that this RG, which controls the gain on the signal, is different for the horizontal versus the vertical signal, but the basic setup is amplification and then a low pass filter for the signal. Yep, as you can see, the vertical signal schematic is basically the same, just a different RG value for additional amplification of the vertical signal. Some hardware considerations that we had while designing the circuit were deciding to implement a low pass filter instead of a band pass filter. We did a lot of research prior to building our circuit, and we found that other groups who had tried to make something similar created a band pass filter because they wanted to filter out the DC offset of the signal. But also by making a band pass filter, you differentiate the signal, and we didn't want the signal to be differentiated so that it would only detect changes in the signal. We wanted it so that the signal would be a constant value when the user was looking in a specific direction, rather than only spiking the voltage when the user changed the direction that they were looking. So that's why we decided to implement a low pass filter. So then we would keep that DC offset and be able to measure it and use that to control the position of the cursor on the screen. Another thing that we spent a lot of time on was tuning the gain value of each circuit, because these EOG signals are really small. So we had to amplify them a lot to be able to see them in our software and then translate that to a cursor position. And then another thing that we didn't end up implementing in the final hardware design was a potentiometer subtractor circuit. We did test it out, but ended up not using it because we were getting unreliable values with it. But the idea behind it is that the potentiometer we would be able to control a voltage that is adjusted to each user and subtract that offset from the signal, so that we would only get the small changes in the signal into our software. And this would be a way of subtracting the DC offset in hardware versus software, but we ended up going with the software-based version of this algorithm. Here is a diagram of our software in LabVIEW, and I just put this whole picture here so you could see a overview of it, but we'll go into each parts of it in detail. So here's the first part of the LabVIEW block diagram. The main things that I'd want to point out from this diagram are the waveform indicators, which you can see on the left image because I pasted the front view panel. We basically plotted our raw signals, and then we also plotted the adjusted signals based on the offset that we subtracted. Here's an example of something that we'd see for the horizontal eye movement. You can see for the first 4 seconds on the time scale, the user is looking straight. Then we instructed the user to look left and the voltage went down. And we instructed the user to look right and the voltage went up. Here is the second part of our lab view. And this part basically takes a scaling value, which is adjusted per user, and translates that signal that we're acquiring into a cursor position. So for every person that uses our system, we have to do a calibration process before they can fully utilize the system. And to the left, you see an image that we use to ask users to follow a certain eye movement pattern so that we could get their voltage values and then calculate a offset and scaling value. So we would ask the users to look like completely left, completely right, completely up, and completely down, and then use those values to set this horizontal offset and vertical offset, which you can see in the top image on the right, and then also adjust the horizontal and vertical scaling values, which is on the bottom right image. And these values just help calculate the cursor position. Here's a little image of our testing setup. So this was one of our lab mates, Aiden, and he has his electrodes hooked up to our circuit, and we had him looking at a screen, and we would instruct him to look specific places to test our system. Here is a quick demo of our system looking to horizontal extremes and intermediates. So the cursor is in the middle of the screen right now. We instructed him to look right, and you can see the cursor is slowly moving to the right. Now we instructed him to look back to the middle. Now we instructed him to look to the left, and you can see the cursor slowly moving to the left. We instructed him to look to the middle again. Then intermediate right, that light purple X, back to the middle. And then he goes to the intermediate left X. Here is the next demo of our system going to the 4 corners of the screen. Going to the bottom left corner now. Back to the middle. Bottom right corner now. Now I'm going to talk about our obstacles and challenges. So one of our biggest challenges was the hardware design, and acquiring a vertical signal was a bit more challenging because that signal is smaller in the human eye because there's a little bit more limited eye movement vertically versus horizontally. And then along with that, tuning the gain to the appropriate sensitivity and doing different tuning for the horizontal signal versus the vertical signal. Next was balancing complexity and accuracy. In our hardware design, like I said, we tried that potentiometer circuit, but it ended up being better to just subtract that offset in software. Another obstacle we had was calibration, kind of tuning the scaling value because that would change per user, and then the range of the user offset and making time varying adjustments because the user offset would change for each user, and over the time that the user was using the device, their offset would change. So we'd have to make pretty frequent adjustments to those offset values. And then another thing that we ran into was user fatigue. After testing for so long, the user got tired and the system was less accurate. So our results and conclusion, overall, we think our project was a success. We were able to build a device that identified horizontal and vertical potential differences and converted these values to a cursor location. We were able to move to extreme and intermediate horizontal values as well as to the four corners of the screen. And although our system had some error, it would often go to the general desired location, but not to the precise location that we wanted the cursor to go to. Our next steps would be to streamline the calibration process, make that a little bit faster and maybe automate it, and then possibly do calibration using vocal commands because right now we were inputting in the offset values via the keyboard, but if someone were to use the system that wasn't unable to use their hands, then it would be most beneficial to have this process available using vocal commands. And then along with that, adding a feature to turn off and run the system using vocal commands for the same reason. Also, we would want to test more so that we could adapt to different screen sizes because we were only able to test with one screen size. And then lastly, add a way to click the mouse using possibly blinking is what we were thinking. And yeah, that is what we were thinking for the next steps. And thank you so much for listening to my presentation. If you have any questions, feel free to contact me by emailing me at my email address down here or commenting on this video. Thank you so much.